So yeah, my name is Atha, and yeah, thank you for inviting me to the workshop. I work at Photonic Incorporation, which is a quantum computing, a silicon-based quantum computing company based in Vancouver, British Columbia. The topic I would be talking about is more on the practical implementation of the quantum computation schemes, and there's more on the system which we are concentrating on is silicon. So just to kind of give you the kind of overview of what I would be talking about is would start with a brief survey of all the different platforms which are in silicon, and also kind of like to motivate why silicon might be one of the most important system for quantum computation development. The talk later on would be mostly concentrated on T-center to silicon, which is the technology which Photonic Incorporation is using to implement quantum computation in a photonic-based silicon quantum chip. So that's the a bit of the physics about these T-centers, how the spin qubit is realized, what is the spin photon interface in that system, and how do you characterize the qubit performance and initialize the qubit, how to do the full ground state spin control. And the last part, I would try to kind of concentrate more on our practical implementation of distributed quantum computing with these T-centers. So this is an approach which Photonic Incorporation is spearheading or more concentrating on, is to move towards distributed quantum computing and to have systems which are more network-based, quantum network-based. So just to start with quantum, so as a physical implementation of any quantum computation scheme, you have to fulfill a few criterions which are well defined by DiVincenzo's criterion. Is you should have a well-defined qubit system, well isolated from the environment, to be able to initialize the system, should have long coherence times. So hello?
Can't see your slides.
Oh, you can't see my slide. Sorry.
Maybe it's frozen.
Just a minute.
We see your first page, the title page.
Oh, you are still stuck in the first page. Okay, let me stop sharing and start again.
Okay.
Sorry about that. Can you see it now?
Yes, but smaller.
It's smaller still. Yeah. Wow. Okay. Sorry about that. Let me. Still smaller.
Yeah.
Wow. Okay. I don't use Zoom, so kind of bear with me, please.
Okay. We can continue. Okay, we can continue. No problem.
Yeah. Okay, it looks fine. It says okay. Yeah. So I hope it's fine now. Is it better now, or is it's working for you?
Yes, it's working.
Okay, good. Okay, yeah. So I go ahead. Yeah, thank you. So the criterion are well defined in terms of the physical implementation for quantum computation. that to have a two-level system, to be able to initialize it, to have long enough coherence times, to have a set of universal quantum gates being to be implemented, and also to be the ability to read out the quantum state with high accuracy. So the different dominant computing technologies which are currently like in practice or in commercial practices are like mentioned here, kind of a brief summary of them. Like there are of course the superconducting qubits, and the trapped ions are kind of the more advanced techs at the moment. Then we have neutral atoms and cavity QED, which were kind of the start of the quantum revolution. And now the new players or platforms which are being added now are the silicon and the quantum annealers. So, and also the photonic quantum computing. So this is kind of like the different technologies which are kind of aiming at getting better and better at those criterion required for quantum applications. No, to have any meaningful quantum computing system, the most important thing is the scalability of the system. So the scalability, to have a quantum advantage, scalability is definitely the most crucial part. But tied with that scalability is the ability to design and implement that the scalable system with high enough scale, so that like it's really practically implementable. And then the important thing is, because for a larger system to work in a practical way, you need to have the ability to have error correction. So not only the qubit errors have to be as small as possible, and on top that you should be able to have a large scalable system with those high quality qubits at the same time. So when you think about such systems, like building about such system, you can think about a module of a quantum computation, and you can add more and more qubit to it to make it like to have a large scale quantum computer. But there's a limit to what you can add to such a computational module. So what you can think about then is then kind of a networking system in which you have these modules scattered around, connected with each other horizontally. And that seems to be the way forward to have large scalable system, because those conditions in which you want to cram more and more qubits in a single module seems to limit, it has a limit to which you can add more and more devices on a single module. So it has to be a multi-modular system network with each other. So the quantum networking seems to be an integral part of any practical system. And this kind of necessitates the importance of photonics and the photonic interconnects. So as a kind of a conclusion, to have a large scalable practical quantum system with modular activity, silicon seems to be the best choice, mainly because silicon is the most advanced scalable material we have at the moment. And any physical implementation of a large scalable system, whether it's quantum, will have a big boost if you use all the scalable the approaches or the advancement we have done in the fab, on the fab side for the classical logic in the last few decades. So all that improvement in the tech on the material side, on the fab side, that gives a huge advantage if we are able to do quantum computation on a silicon platform. And at the same time, you have silicon photonics, which started a bit late, but this is something which has caught up really fast. And we have very high quality, highly dense silicon integrated photonic circuits available now. So just so for the scalability argument, the classical computing, the scales with which classical computing has increased over the past decades has so that we are able to have devices up to 4 or 5 nanometer sizes is something which the quantum hardware should also aim for. On the silicon photonics, we have like, so one can think of an integrated circuits, which is not only add all the photonic components which are recently developed, like which has been developed on silicon platform, like optical, like waveguides, couplers, photonic crystal, cavity modulator, and so on, and to add not only light sources, which can be lasers, or also can be quantum light sources, like and also at the same time adding detectors onto the same circuit. So what one can aim is for a highly integrated circuit which has not only the circuitry component of the photonics, but also the sources and detectors. So just to give you an idea of how fast the advancement in silicon photonics has been, is like it caught up pretty late, but it's like the scalability has achieved is pretty fast, and much like it seems to be better than the other competing systems at the moment. So these really give a big argument in favor of going for silicon for quantum computation. Now concentrate on silicon. What are the different platforms which have it's already been used by different in different ways for quantum computing, and different platforms exist for quantum computing based on silicon. For example, the photonic quantum computing approach, which is a measurement-based quantum computing approach, utilizes the interferences, like the bosonic interference, and uses a measurement-based computing approach as one way in which quantum computing is implemented in silicon, in which you integrate. Sorry, can you hear me?
Just a moment, please. We see on the page 4, slides doesn't change. Your slide.
Oh, okay. It's still stuck at 4. Oh.
It's not changing.
Oh.
It's not changing.
Okay, let me. I'll start sharing again. It's sorry, I don't use Zoom, so I haven't been able to figure out how it works there. Yeah. So you can see it. Yeah.
Yes, we can see it.
Yes. So if I
slide number 4, we see.
Yeah. So if I go to the slideshow, can you see slide number 5 now?
Yes, now 5.
And 6?
Yeah, right.
And 7?
Hocam
yine bir hata var sanki, o siyah şeyler. Slide'ı da değil. There's a black band, in the middle of the screen.
Oh, really? I don't see any black on my side. Is it? Just a minute. Maybe it's maybe the Zoom is gone now.
No.
No.
Yes, it's gone now.
It's gone. Okay. Yeah, it was just the Zoom bar or task bar or whatever you want to call it. Yeah. Yeah. Sorry about that. It's gonna. Yeah. So yeah, I can. Should I go?
5.
5. Okay. Yeah. So 6. So yeah. So this was about the scale which silicon can achieve by Moore's law, and the different silicon photonic platforms with the ability to integrate not only photonic components but also light sources as well as detector into the photonic circuitry as kind of a big advantage which silicon provide. So yeah, so can you, I'm in page, so can you see my slide 10 now? Yes?
Yes.
Yeah, okay, good. So yeah, so this photonic quantum computing is one of the approaches used in silicon, in which like the which is based on measurement-based quantum computing approach, and which utilizes the quantum interference between bosons as a means, and the subsequent measurement as a mean to do quantum computing. So that's one of the approaches already implemented in silicon. Another approach which has quite a great success has been the quantum dots implementation in silicon quantum in silicon, in which you have a metal oxide semiconductor based device in which you define gates based quantum dots. You apply gates, and the gates define a quantum confinement region so that you can have charge carrier confined there, which defines your qubits. And they have also have shown quite high fidelities, but also integrate readability as well. The third most popular system, like a system which is approach in silicon, which is gaining more traction, is the quantum defects based approach in silicon, in which you have a silicon crystal and you have isolated defects. It can be some missing atoms, or it can be some impurity atoms forming some isolated configuration within the crystal, and which can act as a quantum defect and as a quantum entity, which can be used as a qubit. So examples here are the G centers in silicon, for example, which is a silicon atom surrounded by two carbon atoms, or you have a T center in silicon in which you have two carbon atoms with a hydrogen atom and a delocalized electron in it, trapped in this quantum defects. Or you can have a two phosphorus atoms in certain configuration in silicon, defining a defect system. So this talk would be mainly about this quantum defect side of the implementation of quantum computing in silicon. So what are quantum defects and why they are kind of viable candidate for quantum computing is so silicon, a pure silicon would have your conduction and valence band, but if you have any defects, these defects appear as discrete energy levels within the band gap, or can also be within the band as well. So these are discrete energy levels which has a different character than the band electron. They are more isolated, and you can have a variety of many different such defects, and isolated energy levels can potentially be in silicon. So this is a DFT calculated transition dipole matrix versus excitation energy of the different defects in silicon, which can be so what's important is like you have a large variety of these defects which are available, or which can be used potentially for quantum computing applications. What you need then is kind of like to start with a pure silicon and deterministically induce any defect which you want to deterministically or not determin or probabilistically introduce in your system. Which system or which defect to use would depend on let's say what excitation energy you want to deal with. For example, what would be the emission energy or the excitation energy of that defects. And important consideration here would be you want your two-level system or your quantum system to be compatible with, let's say, the photonic technology of the optical fibers tech, and that's where you want your defects to be in the telecom wavelength. So anything which is in the telecom wavelength is something is of interest. And then the other consideration is the dipole matrix. So you can have high dipole matrix, you can go towards defects which has high dipole moment, which would be like lower lifetime. So they might be more useful for the quantum light sources, but you can move towards lower dipole, smaller dipole moments with longer lifetime. They can be something which are more important for spin qubit application or qubit application. So depending on the system, on the application you want to use quantum defects, you can kind of choose which quantum defects you want to use and engineer that for the potential application. So as an example, I'm showing here silicon, like a G center in silicon, which is 2 carbon atoms with silicon in the middle. And if you can, it has a discrete energy levels in the band gap, and you excite this with above band gap when you see is a very narrow emission from the center. You get high count rates with saturation, and the lifetime, which is pretty small, 4.6 4 to 5 nanoseconds, and you can have good high quality single photon emission from this system. So this is kind of an example of a defect in silicon which can be used as a single photon source. Ideally, we would want them to have these single photon sources to have smaller lifetimes. But for this talk, I'm more concerned with spin qubits in silicon, or how to do quantum computation in silicon. So what I would be presenting on like what T centers in silicons are. So T center in silicon is a defect in silicon, which is consisting of 2 carbon atoms. So one carbon atom is in the interstitial site, and another carbon atom is in the it replaces one of the silicon in the crystal. And attached to these 2 carbon is a hydrogen, and over this whole molecule which we call it the T center, now there is a delocalized electron as well. So what you can think of this system as consisting of 2 spins. One is the electron spin, and one is which is the delocalized over the whole molecule, the T center molecule. Another is the proton, which is the hydrogen spin. So looking at the electronic structure, this is the ground state of this. So from the DFT, you can calculate the ground state of this T center configuration, and it using all the like the electrons in this molecule. And what you have is the ground state looks something like this, in which you have this is the spin up, and this is the spin down species. So what you have is, if you look at this configuration, you have a net electronic spin in this system, which is this one, which is an unpaired electron spin. So the ground state is a spin singlet in this case. So the excited state, if you excited, has a hole as so you have all the electron spins are paired, but what you are left with is a hole, because one of the electron which is excited up there left a hole here, and a hole has a certain spin. So the excited state in for this T center is a hole with a spin 3/2, and that hole is split into 2 energy levels, Tx0 and Tx1, due to the internal strain in the system. Now what you have is, you can have a well-defined 2-level system given by the ground state, which is a spin singlet state, and the excited state Tx0 energy level, and the energy difference between is 935 millieV, which is the telecom O band. So you do have here a system which you can excite it, and which can emit in the telecom wavelength, and which you can control by light of a telecom wavelength, and which provide potentially a spin singlet ground state and a potential spin qubits possibility. You have a lifetime here, and the lifetime for this case is pretty long, more than 900 nanosecond, and this gives you the ability to have longer coherence time as a prerequisite for a spin qubit or a qubit system. So you can apply a magnetic field to the system. So you have the ground state split into the spin up and spin down electron configuration, and the excited state splits into multiple spin components. But what you can do is you can concentrate on energetically by choosing a certain frequency of light to only have the to deal with only the whole up and the whole spin up and the whole spin down energy state. So you can choose energetically what you want to excite in the excited state, and you can choose it to be the whole spin up and the whole spin down in the excited state. So the overall electronic structure in the presence of the magnetic field looks something like this. You have the ground state, which is a spin singlet. You have the excited state, which is the hole, and then you have the electron and hole having a different gyromagnetic ratio. So you have a different splitting of the ground state and excited state in the presence of magnetic field, and you have the hydrogen atom spin as well, which is the nuclear spin. So you have a hyperfine splitting on top of these fine structure as well. So you have this whole spin manifold, which you can then control by the microwave and RF frequencies to control the ground and the ground state whole electron, not only the electron spin, but also the whole spin in this T center. And I would show how this control is achieved. Just to give you an idea of like how good this T center system is. So normally, if you think of two-level system like this, which is a defect, and defects are probabilistic defects, so they're formed on its own. And if you look at, let's say, if you implant the carbon and hydrogen into a silicon, and you have an ensemble of such defects, and you try to probe that by photoluminescence, what you see are these excited state and like the TX0 emission and the TX1 emission, and then you also see these side bands. If you zoom in on this region, which is the two-level system emission within the telecom band, you can have it is pretty narrow if you are in the natural silicon, but it becomes much narrower if you have a silicon platform which is made of 28 silicon, much isotopically pure. So you have a distribution of these T centers which is ultra narrow, and all these all the T centers, or most of the T centers in the distribution, would lie in a narrow distribution of somewhere between 10 to 15 gigahertz. So compare it to all the other two-level system like gallium arsenide quantum dots, which has a distribution which is much broader than this, for example. So you have a two-level system which you can implant into silicon, and still and the implantation give rise to a T-center distribution, which is a probabilistically formed under favorable condition, and still you have a distribution of these two-level system which is pretty narrow. So this is something which is highly important. So consider you have a silicon SOI platform in which you have defects distributed within different devices, and all of them have energies pretty close to each other. This is extremely important if you want to implement, let's say, qubit to qubit interaction, because you want two different qubits to have energies as similar as possible. So how do we kind of in photonic how do we implement a photonic silicon-based photonic chip? Is we have optical cavities, one-dimensional Bragg optical cavities. We have these implanted T centers embedded within these devices, and that is within a chip, which is a silicon based chip. And on these chips, we also have optical switches, and also we are aiming to add SNSPDs on chip detector as well on the same chip. So what you have is something which looks like this. You have your T centers, which are within a mode volume of your one-dimensional Bragg cavity, which you can excite by grating coupler. So you have laser, which can couple into the grating coupler, excite your your quantum defect within the cavity. And then you can have, on top of that, you can have apply a static magnetic field and a B1 field, which is the microwave or the RF field to control the spin population via microwave RF field, which is achieved using by PCB to chip wire bonded circuitry. So what you have here is a full platform in which you can have not only optical access to your two-level system, but you can also use microwave and RF on the same platform to control the spin of the qubit. So this is kind of the integrated nanophotonic chip which Photonic Incorporation is working with. So how do we work with T-center as a spin qubit, and how do we realize a spin qubit? Remember, you should be able to initialize control and then read out the spin qubit. So first, on how do we prepare this a specific spin state? So you initialize. So let's say, how do you initialize your spin state? So you have your ground state electron spin singlets and your whole excited state whole states. You can spin select a specific excitation, drive it, and so you have a strong higher probability of transition. So you would have a cyclic transition between these two states. But there's a very weak probability of this cross transition. Nevertheless, there is some probability there. So you keep on. So if you are constantly pumping the system, there is a probability that the system after some time ends up in this state. So you would not be able to get any photon after that from the system, and the photon has gone into a dark spin configuration. But this gives you so the T centers become dark. But what you have done this way is you have transferred all of your population into this specific spin state. So this is kind of this kind of a spin shelving can be used for is being used as a very efficient way of spin state preparation. There's a kind of a trade-off between how quickly you want to prepare your spin state and how long you want to do subsequent spin control cycling on it. So for example, if this transition is relatively stronger, so the spin initialization is faster, but the problem with that is that you are not able to do subsequent spin control because the cross transitions are more dominant. So you would not be able to do spin control mechanism later on forward. So there's a kind of a trade-off between the cyclicity and the spin shelving. So this is a demonstration of how after how many optical pulse cycles. So what we use is optical pulses to excite and to detect. And so you run the system under several excitation pulses, and after some pulses, the probability of the detection from the photon from the two-level system decreases exponentially. That's where you know that you have prepared your system. And the fidelities we have for this spin state preparation is more than 98%. So now you want to, once you have prepared your system in a certain spin configuration of the ground state, you want to control it. And the control, for example, you want to control the electron spin. and the control is done by the microwave. So you have your cyclic transition by a certain laser, which prepare your system, let's say in this spin configuration, which is the upspin electron. Then you you apply a pulse. You shouldn't see anything, but then you apply a microwave, which is a microwave resonant between these two transitions, and you increase the pulse width of that microwave. You should start seeing electrons. The system was initially dark. It become because of the microwave, you start equilibrating the population of the up electron and the down electron, and that results in any as you increase the pulse width. So as you increase the pulse width, that population equilibrate, and you start increasing the emission from or the photon which comes out of this two-level system. So once you have and you can adjust the pulse width to completely transfer the population from the ground state to the excited state. So this is and then you can so as you can see here, you can have like we have very good control over the spin. You can you can now do measure the spin coherence of the system by the Ramsey kind of measurement, in which you prepare your system as a starting point in one of the spin state, apply a pi by 2 pulse, then wait for some time, and then apply a pi by 2 pulse again and measure the emission again. So so for this way, the Ramsey measurement gives us a T2 star time of 22.8 microsecond. We do Hahn echo on this system as well, which again, in which you refocus by a pi pulse after pi by 2 pulse excitation, and that Hahn echo give us a T2 time of 270 microseconds. So these T2 and T2 star times of this electron spin is one of the longest solid state spin coherence times measured in a solid state system. And it's given that it's a chip which is a photonic integrated chip. This is kind of one of the first such demonstration in a full chip based system. So you can similarly have a control over the nuclear spin time, nuclear spin state as well. So what you can do is, for that you have to use an RF. So you initialize your stem in one of these hyperfine split state, and then you apply RF, equilibrate the population, and then you can have by just changing the pulse of the pulse duration of the RF pulse, you can have a population transfer between the nuclear spin up or the nuclear spin down electron state. You can do a nuclear Ramsey and a Hahn echo, and you get very impressive nuclear spin coherence times there. So again, so you have a system which has two different qubit in just one in just one defect, an electron spin which you can control and a nuclear spin which you can control. So this gives you a very a big advantage of having these two qubits, with both of them have longer coherences to attain something like, let's say, control NOT gates or 2 qubit gates. So and the other important the good thing about the system, like the emission and the control of the whole spin photon interface, is in the telecom band. So you can not only do an inter-chip photonic communication, but also between chip to chip photonic communication over optical fiber. How much time do I have? Sorry, I just lost track of time a bit.
15 minutes, 15 more minutes.
Oh, 15 more minutes. Okay, thank you very much. Yeah. Any question up till now? Or Or should I take question at the end?
Yes, one question.
Yes.
So when you, yeah. Oh, yeah. Hi, sorry. So my question would be, when you measure this electron spin T2 times, does
Yeah.
that correspond to the lifetime of the spin in the excited state, or is it something different than that?
No, it's different. It's different. So the excited, so it's just a lifetime. This is the time in which gives you a measure of the loss of the coherence. So for example, let's say if you initialize your system into like after like you in a certain spin state, then you apply a pi/2 pulse, it is in a superposition state. And the superposition state is like it's, let's say, it's a pure superposition state, but because of all the decoherence phenomena in a solid state system, just like phonons or like charge carry, like charge scattering and all those different phenomena, what happens is that the coherence is lost, and you're no longer on the Bloch sphere surface. You're like so this T2 time is a measure of the loss of that coherence. So it's not the lifetime. I hope it's
maybe I can ask one more quick question.
yeah.
So it's actually very similar to the defect centers in the diamond, in the carbon. It's almost like the reverse of it, like the carbons and silicons are like.
Yeah, exactly. Yes.
But my question is there a benchmark, like, for example, zero phonon line or something like that, to compare these two platforms? I guess the main advantage is it can be implemented on chip because it's silicon, but is there a way to compare their
I mean, that's the ability to fab silicon in such a small and integrate it so easily is a big advantage for T-center in silicon, like compared to diamond. Diamond is hard to fab and hard to integrate. Yeah, it's still, I mean, there are progress there, but yeah, I mean, nothing can compete with silicon in fab. yeah. So, okay, going ahead, I don't have much time, but so the next thing I want to move toward is the distributed quantum computing. So this is something which we want to is kind of aiming for is, and the important for this is mainly scalability. So you are restricted by the number of qubits you can put in one chip, just by the ability, because you cram more and more qubits into one chip, and there's a limitation. You want your chip to be as isolated as possible. So the limitations come from that requirement that you want to minimize decoherence. You can't cram more and more. So there's a limitation on this. So the best approach, or the approach which might work later on, would be that you split the system into modules. Don't cram each module, but you should have the ability to interconnect different modules at the same time if you have good T-centers or good qubits on either of the modules. So this is the kind of the the scalability approach we are aiming at to achieve fault tolerance logic quantum computing. So what we think is there has been like different stages of quantum computing. With the first one was the noisy intermediate scale quantum computing, which was in which you were dealing with single qubits, each one noisy enough that you couldn't have enough error corrections. Then this is the next phase, which is currently in kind of a practice in which you have small scale qubits in which you can have achieve error correction using logical qubits. So logical qubits are not your single physical qubit, but they are interconnected qubits in which can talk to each other by entanglement, and you can have a small scale entanglement based logical qubits, which provide you the ability to do error correction as well. The next approach would be something like you have two different different modules talking to each other, each achieving error correction locally as well and having logical qubit locally. So this is kind of the network-based approach which we are aiming towards. So for us, the important thing is like we have a silicon spin platform which is telecom compatible. So you can imagine thinking of using optical fiber-based network between different chips to just communicate and establish this quantum entanglement between different modules. So, so I would go a bit quick now. So, want to show you how do we establish such logical qubit operation between two different T centers located in two different crystals. So if I go back here just to give you an idea of like how the system looks like. So you have these different crystals, each is loaded with one of such chips, and these crystals at 1 Kelvin. And you can have interconnect between the different crystals. These can be optical switches. These can be all the other controls of electronic controls, mostly at room temperature, and they're connecting these room temperature controls connecting different crystals optically and electronically. So imagine you have two different chips, one in each crystal, and both have T centers. So let's say, and then you scan your laser. So you apply a magnetic field, which is, let's say, some small magnetic field, so that you can see your electronic structure splitting, the fine splitting there. So here are shown are the PLE spectra on the two T centers. So the red one is from the one crystal, the blue one is from the other crystal, and you have these different transitions possible, which are called as like B, A, B, C, D, 4 different transitions, because you have different gyromagnetic like ratio, G hole factor of the hole and the electrons. You have 4 different transitions possible, but let's say we are probing 2 of these, which is the B and C. So what is shown here is we have made resonant the B transition on one T center to the C transition of the other T centers. So this kind of configuration, so we have 2 T center resonant with each other in such a way that one transition of one T center is resonant with the other transition of the other T center, located entirely in 2 different crystals, both having similar line widths as well. And this is kind of the configuration we start with when we want to establish a logical qubit between these 2 distinct T centers in 2 different crystals. We characterize them by their lifetime. So the lifetime, you can see, instead of 940 nanoseconds, the lifetime on both T center is 65 or close to 60 nanoseconds, indicating that you have hypercell enhancement in the cavity, and both of them have less than 1% of background on the G2, meaning that both of them are single emitters or single quantum defects. So what you can do is you can switch on your microwave and tune your microwave while having your control laser still on B and C. So when you tune, what you can see is like you can equilibrate the population between let's say the spin, this state and this state, which is the hydrogen up spin state, and the electron up and the electron down. So if initially your state was prepared in such a way that it was dark, after the microwave it would become less dark, and you would see at resonance, you would see a high emission. Then become dark again, and you will see emission again. So you have these two peaks corresponding to, when you tune the microwave frequency, one corresponding to the hydrogen spin down, and one correspond to the hydrogen spin up. And you can then, let's say you start, you concentrate, you park your microwave here on this frequency, and then to change the pulse duration of this microwave frequency, and you can have these Rabi oscillations. So what if you are at this point, what you have done is you have transferred all of the population from this state into this state, which is from a whole, which is from a spin up electron to a spin down electron, while the hydrogen spin was up. So this is a control NOT gate in which you invert the population, invert the electron spin state if the hydrogen spin is up, and you can do vice versa for the other state as well. You can not only achieve this, but you can also do the same for keeping the electron spin constant, but toggling between, by RF frequency, toggling between the hydrogen spin up and the hydrogen spin down, achieving very high fidelities with such kind of a controlled NOT gates. So this is a demonstration of the controlled NOT gate with this, and you get very impressive T2 star and T2 times with such T0 gate implementation on this system. So what we demonstrate with this is a specific protocol to establish the entanglement between these two qubits, and that is the Barrett-Koch protocol, and to demonstrate the full performance of a CNOT gate. So it involves the initialization of two qubits in two different clusters. Then you prepare them in the superposition state, each one of them in superposition state, excite them after superposition, being in a superposition state, get the photons out of that system after excitation, interfere them on a beam splitter. There's kind of a Hongomandel interference. Whatever you get, you invert the state, and then you do another optical invert the state by a pi/2 pulse, by a pi, and then on each of these local systems, and then apply another optical pulse and detect the photon via beam splitter again, and measure the correlation after the beam splitter. So this is kind of the Barrett-Koch protocol, a well-known protocol to demonstrate entanglement between qubits. So this is the system we have, two different cryostats excited by lasers with pulse excitation. Pulses go to either of the cryostat, and we have these different controls. So, and the photon which comes out of them are then interfered on a beam splitter. So there's a Hongomandel interference between two spin qubits in different cryostats. You can see when so what you can make, so you can play with the delay between the pulses to make the photon distinguishable or indistinguishable in time, and this is the Hongomandel interference between the indistinguishable and distinguishable coincidence events. We get from here, you can calculate the visibility. What we are doing here, restricting ourselves to specific bend times in the detection because of the spectral diffusion. You have your 1 gigahertz of spectral lines, but you have spectral diffusion with this. So what you do is, like, you want to limit your bend size just to have the higher, to avoid the the spectral diffusion coming from spectral wandering. And as a function of the bin size, what we can, let's say for the smallest bin size, we can achieve visibility as high as 63%. The problem with this is, like, you can there's a trade-off between the bin size and the rate at which you get these entangled photon pairs. is like you increase the visibility, but you end up decreasing the 2-photon count rate. From this visibility, you can estimate the upper bound Bell state fidelity for in this case, and in this case 96%. You can demonstrate the full protocol, and after the full protocol, which requires a pi/2 pulse after the Hongo-Mandel effect, and then a basis selection, and then final readout, what you get is a Bell pair fidelity of roughly 53% at 40 bin size, which is more than what is required to show the to break the classical limit. So we have demonstrated this way that you can really entangle two different spin qubit in two different clusters. So this this is a demonstration of a specific gate, which is a CNOT gate, again a universal gate, in which you establish entanglement, which is based on the entanglement consumption between two different electronic state in two different qubits. So this is the teleported CNOT gate. What we have is a version of that gate. A demonstration is something like this, in which we do a certain kind of post-selection based on this first measurement. So this is a post-selected teleported CNOT gate, which we demonstrate here, which is one of the first demonstration in a solid-state qubit system. So this is, so by changing the input, varying the input between of the initial states, you can construct a whole truth table, and which demonstrate that you have an operational CNOT gate using this configuration. So just to conclude, we show that T-center can act as a highly efficient spin qubit system with very efficient spin photon interface, which can be used to actualize modular architecture of quantum computing, in which you can realize a logical qubit between two different qubits and establish entanglement between them, and establish and show the full function of a CNOT gate. So with this, I would like to thank, and just a bit of advertisement about Photonic. So this is a Vancouver-based company, more than 140 members. It's distributed in Canada, US, and Europe, and it has recently gotten, last year, it got in partnership with Microsoft in quantum networking. And what we are aiming is a scalable quantum computing with utilizing quantum networks. So the approach we have is to realize a network-based quantum computing, even for demonstrating simple logical qubits. And the ability, and we're also working towards fault-tolerant quantum computation and working at different states. So with this, I would like to thank you, and I'm open for any further questions.
Thank you very much.
Yeah.
Thank you very much, Professor.
Yeah.
We
Thank you
have
too.
this isn't working. It's not working.
Can you hear me? Hello?
No,
Oh yes, I can.
Yep.
Yeah.
this one, this one
No
working.
problem. We can hear. Thank you, Dr. Haq, for joining us this week and giving this interesting presentation. Does the fact, that silicon, has an indirect band gap,
Yes.
how does it affect the performance of the single photon source?
Yeah. So that's a good question. Sorry.
High photon absorption in silicon substrate, how does it affect the performance?
Yeah, that's a good question. So it does affect it, but what we are using is a silicon insulator platform with waveguiding, which kind of achieve a very good collection efficiency out of the chip. So with good optical design, you and the choice of the substrate you are using, you can get because what you have is like your mode stays in the silicon on insulator on top of the chip, and you can use the waveguide to guide your light more efficiently into your grating coupler, which if nicely designed can give you a very good like very reasonable collection of light from the chip itself. So maybe not as good for a single photon source, but good enough to demonstrate a spin photon interface for spin control.
Thank you.
Yeah.
Right?
Yeah.
Awesome.
You must stop. We have one more question.
Yeah, sure.
So my question is, at the present, how much qubit can you operate at the same time with this distributed networks, or can I say nodes? I don't know. But and in the future, is there like a limit of the qubits that you can achieve with this kind of distributed architecture?
So this is like this was our first demonstration earlier this year of demonstrating this logical qubit between two disparate qubits in two different cryostats. So this is our current state of the art, but what we are aiming so there are two things which we are currently working on. One is to improve the performance of this logical qubit, and that can be done by reducing the spectral diffusion. So any two-level system would have some spectral diffusion, which would mean that the frequency would wander about in time due to different decoherence mechanisms. So we want to reduce that to get higher fidelities on these logical qubits. And so at the moment, we have only demonstrated 2-qubit gate. I mean, we can in principle do more. What we would like ideally is to improve the performance, and at the same time the ability to have not only between 2 qubits in two different modules, but also multiple qubits. And so in principle we can do that, although we haven't demonstrated that, but we can definitely do such logical qubits between different qubit on let's say 2 chips, for example. So that ability is there, and that can be scaled up not only 2 but more, although it would take a bit more time. And if we have, let's say, if we improve our coherences, that kind of operation become much more easier and to achieve. So this is kind of like what we are at the moment. We can't predict how long would it take, but like we are on the path to achieve multi-qubit entanglement via this way.
Okay, thank you. And
Yeah,
maybe one quick question: is your aim also do the distributed quantum computing while also building a quantum network?
Yeah. So the qubit itself is a quantum network. That's important to know. So it's a qubit. So the qubit operation, so the whole CNOT operation I showed, it relies on 2 qubits talking to each other via a quantum network. So we are already, even with this simple demonstration, we are already showing that quantum networking capability of the system itself.
Okay, thank you.
Yeah. I mean, it would mean that you can establish entanglement. That's what Bell pair threshold would mean, that you can establish that entanglement between two different And that's the essence of quantum networking. Yeah.